All right, hey AP Chemists, this is going to be our next video lecture in Unit 1, Part 5. This is Coulomb's law and effective nuclear charge. This is so important. In class, we did talk a bit about Coulomb's law, if you have a little bit of notes there. It's the potential energy, the energy kind of like holding things in place, of two charged particles depending on their charge. And so we will see that like charges, or we have seen that like charges repel, unlike charges attract, so a positive is attracted to negative. The magnitude or the size of the interaction between the charged particles increases. So the attraction increases as the charges increase. And so just to kind of refresh your memory, this is an equation. This is more like in physics. We are not going to have to use or calculate with this equation, but the attraction, Fe, the force of attraction of an electron, is related to this constant times the product of the two charges, so Q1 and Q2, divided by the distance. That means the larger the distance, the smaller the attraction that two particles are going to have for each other. And we'll also, so that's why R is on the bottom. We'll also see larger the charge, greater the attraction. So keep that in mind for us here. So we're going to skip on down looking at like electrons and protons now. So let's look at the hydrogen atom here. So I have the one proton in the nucleus of a hydrogen atom, and I have an electron, and I have a photon with certain energy that's going to be used to try and remove or eject this electron. That's known as ionization energy. A question here says, what force of attraction holds the electron in the hydrogen atom? Well, the only thing holding this electron will be the force of attraction from the proton in the nucleus. From proton in nucleus. What type of energy needs to be overcome to remove an electron? And I'm just going to say vocabulary-wise, it's potential energy. Potential energy is the amount of energy used to keep something in place, or for our electrons here, it's to keep the electrons in an atom. Kinetic energy is the energy involved in movement or having an electron move. We'll talk more about that at a later time. So according to Coulomb's law, how might I affect the amount of energy it takes to remove that electron? More protons in the nucleus, greater attraction of electron for nucleus, and that will result in more energy required to remove. So just putting some notes here with some questions for us to think about. Atoms that we know in chemistry have a different number of protons. If I'm going to have more protons in that nucleus, the electrons are going to be more attracted to that nucleus. But we'll see some changes to that. Let's consider the helium atom that has two protons and these two electrons. Would the force of attraction holding the helium electrons be greater than, less than, or equal to justify using Coulomb's law? I'd like you to try and answer that question on your own with the information that we have here. Let's talk more about Coulombic attraction within elements in a periodic table. So within a group, that's up and down. Group is a column. Look at our little arrows here. The thicker the arrow, the stronger the attraction. The thinner the arrow, the weaker the attraction. And then we have like this medium thickness, which is medium. So look, I have lithium, sodium, and potassium. This is all group 1 elements. And so I kind of put some information here for us. Lithium has 3 protons in its nucleus, sodium has 11 protons, and potassium has 19 protons in its nucleus. We would expect that more protons would mean that it has a greater attraction. But we could clearly see that these atoms look a little bit different. As you move from the smallest atom, so this is the smallest, we can clearly see it's the smallest because it's the smallest ring. So it's the smallest because it's the smallest ring. This is the largest atom because it's got the largest set of rings here. How does the distance between the outermost electron and the nucleus change? So here is the outermost electron. We call that a valence electron. We'll get to that later. And here's a nucleus. It looks like it's further away. Further away. The larger the atom. So it looks like this electron on the outer end, I'm just going to circle this one. This electron is the furthest away in potassium than it is in lithium. Okay, as you move from the smallest to the largest, how does the attractive force between the outermost electron and the nucleus change? It decreases. How do I know? I'm looking at that arrow, my data here. I have a really thin arrow here. I'm going to use a different color. I have a really thin arrow here for potassium, and I have a really thick arrow for lithium. So there must be something causing that. How is this observation consistent with Coulomb's law? Well, we're going to use distance. That R value, that R squared value in the equation here, the R squared being in the denominator, just to remind you of that. Larger the distance, the weaker or smaller the attraction. So that's something for us to keep in mind. If I have some very large atoms, it's not going to be attracted as much. What if I had within a period, which is left to right in a periodic table, I have sodium with 11 protons, aluminum with 13 protons, and chlorine with 17 protons. Look at this now. The size is about the same. Size is about the same, like not dramatically different as in the previous example. So let's keep that in mind. Can the differences in the attractive forces shown in the arrows be explained by the change in the distance? No. Because look, this distance is about the same. Because the distance is about the same. Oops, sorry. And so now our next question here says, can the differences in the attractive forces shown in the arrows be explained by a change in the number of protons? Yes, that's the only thing that's different. More protons for the same distance, greater the charge, and thus greater the attraction. I'm going to work backwards here. We could see that because look at this chlorine. It's got a thicker arrow. It also has 17 protons. 17 plus is its positive charge. 13 plus, and then 11 plus. And so the 11 plus has a thinner arrow this time. The only reason why this must be true is because the chlorine's protons, there's more of them, and it must be attracting in those electrons more. So now let's talk about the Coulomb's law in real time with something called effective nuclear charge. So the effective nuclear charge, and OMG, so important. I need you to write that down. We need to know this. This could explain everything and anything, right? Is the actual nuclear charge experienced by what we call the valence electrons. These are the electrons, the outer shell electrons. That's what valence electrons are. So we have core electrons, which are on the inside. They kind of do something called screening or shielding the outer electrons. They screen or shield the outer electrons from the nucleus. And so I have a little example here. Here's sodium, 11 protons. The inner electrons, the ones that are in the lower energy levels here, are these 10. 10 electrons are on the inside. It looks like I have one electron that's in the valence or in the outer. And we could talk more about this in class. That one electron is being shielded from the nucleus by these 10 electrons. So I'm going to have to like kind of circle it over here. But here is the 10 electrons kind of on the inside. And here's this one valence electron on the outside. We could calculate something quickly called an effective nuclear charge, like what the charge of this one electron's feeling, by using this quick equation. Z effective, which is known as effective nuclear charge, OMG know this, is the atomic number, or the number of protons, minus the number of core inner shell electrons. So if I'm going to calculate Z effective of this 3s1 electron, like what charge is it feeling? It's feeling 11 minus 10 plus 1. Oh man, there are 11 plus in that nucleus. It's only feeling a charge of plus 1 compared to plus 11. This is weakly attracted to this atom compared to the other electrons. That's big. I have other examples here, but I do need you to fix something. I'm going to skip this down. Can you skip over here where it says, however, the 5 electrons? I have a little typo here because I copied and pasted too much. It says the 5 valence electrons, remember, valence is outermost, see an effective nuclear charge of plus 5 because the 2 inner shell electrons screen or shield some of the charge. So that should be plus 7 minus 2 plus 5. This is for nitrogen, and here's nitrogen right here. And I kind of highlighted the core inner electrons. There are 2 of them. There's 5 on the outside. There's a 7 plus. If I want to get Z effective, it'll be the total number of protons or the atomic number minus the core electrons. Those are the ones on the inside, the lower energy level. That's plus 5. And you could also read the carbon one on your own. I want to end with talking about shielding just one more time and then just our overall trend for Z effective so you can remember. So shielding, again, this is what's known as shielding. For multi-electrons atoms, electrons experience a positive charge from the nucleus and a negative charge from nearby electrons. That's repulsion. The repulsion of one electron by other electrons, thus blocking, I call it blocking the nucleus, we call that shielding. So here is a lithium atom. There are 2 electrons that are kind of blocking the 3 plus on the inside, and then there's this 1 electron on the outside. It's saying it's experiencing a net charge of plus 1. I want to calculate that. And I'm going to skip all this reading here because this is a repetition. I wanted to calculate this again. Z effective is the effective nuclear charge. Z is the actual nuclear charge. That's just known as the atomic number. And you might remember this from our summer work. And then electrons in the core, these are core electrons. These are the electrons in the lower energy levels, right? So if I have lithium is 1s2, 2s1, this is the lowest energy level. So these are the core electrons. That means it's got 1 valence electron. And so if I want to calculate Z effective for lithium, Z effective for that 2s1 for lithium, it's going to be 3 protons, or 3 is the positive charge of the nucleus of lithium. It's got 3 electrons, 3 protons, minus 2 shielding it, plus 1. So this 2s is only feeling a plus 1, where it could feel a plus 3. For AP Chemistry, OMG, this can be the reason for every why question. So things like, why is fluorine smaller in size than sodium? That would be an example, and you'd say something because of effective nuclear charge or the charge and the attraction of the electrons for the protons. I want to end with giving us an overall trend here. The effect on properties from left to right is dictated by charge. So if you go from left to right on the periodic table, you increase in protons for an approximate about same size. Approximate, not dramatically. This means you'll be increasing in Z effective. The effect up and down a group is dictated by the number of quantum numbers, or I'm going to call them shells, energy levels. Be careful for this one. I'm going to go up just to be consistent. As you go up, you have less shells, less shielding, and so greater Z effective. That means the smallest ones are down here. And so overall, we go from up and over to the right. Overall increase in Z effective. Properties that are affected By C effective or ionization energy, we talked about that vocab in class. That's the energy used to remove an electron. The greater the Z effective, the larger the energy. Atomic size we'll talk about. And also something called electron affinity. We'll talk about that in our next set of videos. All right, so for evidence of understanding, either turn in all these notes or do sample problems 13, 14, and 15, so to do here, to show your understanding. All right, if you have any questions or concerns, feel free to reach out.